1, are we tuning into Twitch? Wonder if I can put this microphone like there and it still pick me up. So if you're joining the live stream, you need to tell me if you can hear me. First of all, that's the first rule of any live stream, but we're going to... Oh, I can hear myself. I want to mute. Ooh. Going to be a bit of an echo to start with, but there we go. No output sound, that's all right. Oh no, I can hear myself because I'm muting here. That's all right. Maybe I actually do want my sound to come out of this, as long as I can't hear myself. There we go. So I just need to share this Twitch link. One sec. Go onto the Twitters. Go live on Twitch. Making TensorFlow models train faster with optimized data pipelines. What emoji could we do that? Rocket. Come and say hi. Boom. And we need to, this guy just was 11 years sobriety. That's 4,015 days. Well done, man. I got really drunk on the weekend. Not to take away from that achievement, that's actually very good dedication. But my friend had a party and I decided to get really drunk. So let's if you're joining the stream, please let me know if you can hear me. Going live on Twitch, writing faster, TensorFlow model code. Come and say hi. Boom. All right, let's kick off this stream. So first of all, we'll do what we always do. Today is the 5th of March. Do I want to back up? No. Notifications. How do I turn all of them off? Just show me nothing. So stream, 5th of March, making TensorFlow course materials. What we're doing. We're actually doing a lot of this today. Is make notebook 07 ready for publishing to GitHub. We want fast data loading code. Yes, we do. So prefetch is really fun. We learned about that yesterday's stream. And cache is also really fun. I think this will only work if you have a data set that mixed in memory. And reading the TensorFlow docs on better performance with the tfdata.api. If you're joining, please say hello, and please tell me if you can hear me. Is the microphone good? Well, I think it might be. But let's do this. Yesterday we were working in this notebook. Did this have a mapping function? Because this is something I want to try. Prefetch dataset. We got a very good speed up. So that could be the demo notebook. The demo notebook of how the speed up works. Today though, we want to get this notebook ready for publishing. So we'll come right up to the top. We're trying to beat the food one paper, or deep food paper. It's a top one accuracy of 77.4%. Let's see how quickly we can get our model to run in food vision. milestone project 1. So download the data. We're going to use TensorFlow data sets. Yes. Now I wonder how long this, I'm going to kick this off actually so that we have some data loaded. Running. Do we have a Tesla T4? Topu, thank you very much. Thank you for joining in. And thank you very much for letting me know that you can hear me. I should just do there should be an easy way to audio check. By the way, let me know in the chat. I've been looking into different ways of how to upload these streams to YouTube. Probably not on my main channel, but on a separate channel. So it's just I'm not gonna edit them or do anything. I'm just gonna upload them exactly how they're recorded so that people around the world, if they can't join into it live, they can watch the replay. I'm just gonna upload them end to end. So if that's something you're interested in seeing on YouTube, let me know in the chat. Or if you have any experience of that, if there's someone who does it really well, I'm basically just going to take the Twitch live stream and put it on YouTube. So this is what we did yesterday, actually. We also learned the difference between non-prefetched data and prefetched data, as well as cached and non-cached data. So here's what windows can I get rid of? Okay, we've already got this here. Here's the deep food. I'm just going to get rid of everything except for copy of a copy. Do I want that? I'll get rid of that. And I'll get rid of that. And so this is the course materials, right? The TensorFlow course that I'm working on, my primary focus. I want to get this notebook ready. So this is 07. So that's what we're getting ready right now. Close, close. Okay, let's load some data. This will take a few minutes to run. Orange juice is delicious. That's actually going to be really good if you can hear me and the microphone is just sitting up here, because it's out of the little screen where you can see me, and it's out of the screen where I can see the screen. So this is a great article on TensorFlow. So TensorFlow, the guide typically has like all of these great articles kind of scattered around, and you just need to read one of them every so often to improve your TensorFlow code. But what we're doing here is GPUs and TPUs, what we're using, can radically reduce the time required to execute a single training step. So achieving peak performance requires an efficient input pipeline that delivers data to the next step before the current step is finished. Yeah, so as we talked about yesterday, there's a massive bottleneck. So what's the online whiteboard? Online whiteboard. Who knows an online whiteboard website? Or app? I just want to start drawing on a whiteboard right now. I don't want to log in. Okay, whiteboard, boom. Have I got a drawing? Yes. Okay, here is our problem. So we have, this is a CPU, and this is for deep learning for finding patterns in numerical data. Is slow, right? And we want to go over to GPU, okay? And this is fast. I really wish I had a mouse for this. Fast. Now, where all your bottleneck will be is going back and forth. So we want to, I can just type stuff here. Want to minimize going back and forth. get stuff from CPU to GPU as fast as possible. Now, how do I move this around? Going back and forth. This is actually really cool. Okay, so you see what we're trying to do here. So this is what we're doing. And the functions that are going to help us do this, get rid of that. The functions that are going to help us do this are prefetch and cache. So we use prefetch to help minimize time between CPU and GPU. Okay, so this is what we're trying to do. We'll come back to this later, this beautiful drawing. But everyone gets what's going on, right? We're trying to minimize the time it takes our code to load from data from the CPU to the GPU so that it can make calculations as fast as possible. CPU slow, GPU fast. I'm going to put this over here. This is basically what this paragraph says. This document demonstrates how to use the TF Data API to build highly performant TensorFlow input pipelines. Okay, so let's go through this notebook and see what we have to do. Class names, yes, we can get that. Take, let's have a look. What does an image data tensor look like? Plot an image, wonderful. So I wonder, see, there's one I want to inspect here. Was caching data before mapping. So I wonder how long this mapping function takes. So this is a pre-processing image function. I'm going to can some of the output here so we can scroll through our text and we go here. Here's where our data gets really loaded in, really fast. So RAM, we have 12.72 gigabytes. If you want this article, by the way, TensorFlow data performance. Good morning, Gaurav. What's going on, my man? How you going? By the way, if anyone has any questions, please let me know. Vectorize user-defined functions in a number of transformations, including interleave, preletch, and shuffle, maintain an internal buffer of elements. If the user-defined function passed into the map transformation changes the size of the elements, and the ordering of the map transformation and the transformations that buffer elements affect the memory usage. In general, choose the order that results in lower memory footprint unless ordering is desired for performance. So maybe we can speed up with cache first. So I'm going to delete this because we're not downloading pre-formatted data. I'm too zoomed in to Google Collab. Okay, I wonder how quickly we can increase the speed of this And then the checkpoint, I only want to save the best only. Have I got TensorFlow imported? Yes, we do. So I don't want to save a checkpoint every epoch. So let's go TensorFlow checkpoint callback. This is just on the free Collab, yes. Collab Pro is only available in the US. I probably would upgrade it if I had access to it. Where is Collab Pro available? Collab Pro is only available in the US and Canada. I am in Australia. So saved weights only. Saved best only. When model is considered the best and saves the best model according to the quantity monitored and will not be overridden. If save best, the decision to override the save weights only. Yeah, I think I want to save the weights only. Save weights only. True. Only save model weights, not whole model. Boom. Have we got data? We do. Wonderful. Now let's have a look at what our data looks like. So I have images in the form of tensors, and they have labels in numeric format, and they have class names in string form. The image tensor looks like this. These are all pixel values. Now if we try to plot that image, what does it look like? Takoyaki. Delicious. Okay, now here is an interesting one. How long does this function take to run? So this is what I'm interested in. Do we do batches first, then map? This is an interesting one. Vectorized mapping. Invoking a user-defined function passed a map transformation has overhead related to the scheduling and executing the user-defined function. Vectorize the user-defined function, that is, have it operate over a batch of inputs at once and apply the batch transformation before the map transformation. So I wonder, this is what we could test. Another test. Does batching inputs work faster than... No, which is faster? Here's what we're going to ask. Which is faster? Map, then batch, or batch, then map. I want to turn this off. I like that. You can turn all of the stats off on Twitch. Off. So let's check this out. So right now, I've got a pre-processing image function here that normalizes all the pixel values and reshapes the image. But I'm wondering, Should we batch our images first and then pre-process the images? So see here, map pre-processing function to data and parallelize, or should we batch it first? So the reason why I'm asking this is because of this fast benchmark mapping. So they map, then batch, and then they try to batch, then map, and get a much quicker time. So the only real way to find out would be to try to run this first, and then run the model, and then see if we change it. Yeah. Okay. So let's do that. Run this, run this, run this, run this, run this. Let's see how long this takes. Oh, I should have saved that from before. Do I have that in copy of a copy? Yeah, so this is where a massive bottleneck might be right now. Is I think it's mapping all of the functions right now. So see here, this is what our data is doing. It's taking a very long time to load the first epoch. So this is what I think our bottleneck is right now. How do I? Right, so all of our data is trying to load from the CPU to the GPU. See how it hasn't kicked off yet? It's because it's doing a lot of pre-processing. So that's why I'm thinking maybe I should batch them up first and then move and then map. Yeah, there we go. Look, runtime disconnected. What happened there? Oh, we're back on. This can be code. Plus, this is map batch. Now this is all going to be dependent on what kind of data you're working with, as usual. But it's really good to run these type of experiments so you can work out how your model can be improved. Oh, I got an idea. Why don't we just run these notebooks in parallel? Great idea, Daniel. Why don't you think of that? As always, let me know if the audio is all good. You can hear me. So in this one, I'm going to save these results first in a really hacky way. This can be no mixed precision plus map. Now I'm going to, this is the major key in this one. Change map batch to Now let's get a terminal up. Are we using enough GPU here? Is our batch size? How do we get a terminal? Who knows how to get a terminal window in Collab? I should know this. Tools. Where's the terminal window? Terminal. How to open terminal in Collab. Bottom left. Why isn't... Oh. If you subscribe to Collab Pro, terminal is now available. Yeah, French Toast Mafia. That looks like it is. I need Collab Pro to get a terminal in Collab. Damn. That's okay. Oh my goodness, Chrome is having a big cry at the moment. My computer's frozen. Is this stream still going? Everything is lagging for me. Am I back? Okay, I'm back. My Mac just had a little bit of a cry. So this one we're going to change. So now we're going to train data, shuffle, batch, 32, prefetch. Yeah, I've got no collab option, terminal option here. That's all right. I wanted to run it. So we're going to try batching first. I wonder if this works. And then we will map Holy crap. Mac is very laggy at the moment. This is what happens when you do it dedicated for the stream. And maybe we will prefetch after that. Does it say what order shuffle should come in? Shuffle. And shuffle maintain an internal buffer of elements. Okay. Now, what order does the Bible of machine learning do things in? It shuffles it first, then map, then batch. But I think my map function takes a little while to run. You get me? So we're turning into batches and then we're running the mapping function on batches instead of running it on every file in one hit. If the dataset is small enough and can fit in the memory, you can significantly speed up training by using the dataset's cache method. Okay, I have an idea. So this is what we previously used. So why don't we batch it and then cache it, and then map onto it and then prefetch. Let's try this. Try shuffle, batch, cache, map, prefetch. Now, there's got to be a systematic way to be able to do this, but let's just hack it first and then see if we can figure stuff out by experimentation, and then we can go learn the theory. We'll do the same with the test data, except we won't shuffle it. Anyone know how to get multiple cursors in Collab? Get multiple cursors in Collab. Command Shift L. What the hell just happened there? Oh, it doesn't matter. Just change all these to test. Siobhan's, it sounds like a great idea. Retinal image classification. How much time should you need? Well, it really depends. How far do you want to go with the project? Churros. Yummy. I got prefetch wrong again. Man, all of these typos. Ah. Oh, so I think if I turn it into a batch first. Huh. Okay. So I'll need to, okay, I get what's happening. Because every time I call this, it's adding a batch size to it. See on the front there? Yeah, this is probably, I need to reinstantiate the test data. We're probably, this is all fun, a fun experiment, right? Yeah, see? Oh, that actually worked. None. Now I wonder, oh, okay. We might be on here. We might be on here. Let's see what happens when we start modeling this. So the difference here is that we've put our images into batches first, and then we're going to map. Whereas here, we've mapped on the whole training data set first. So order. This is what we're comparing. Try, map. So does this make sense? This is mapping a pre-processing function to all of our data in one hit, and then shuffling it, and then batching it, and then prefetching it. Whereas in the other one, we're shuffling it first, then batching, then caching those batches, and then mapping, then prefetch. We could probably cache after the map. That might be a better option. Because why would we cache? Because the map is the biggest bottleneck, and we're trying to cache the bottlenecks. Does that make sense? Remember what we're trying to fix here, CPU to GPU. Well, let's run this anyway and see if it works. That's the motto of computing. Cache the bottlenecks. Anywhere where you have to transfer data, not good. What's the motto of computing? Cache the bottlenecks. So this is the scores we're trying to beat over here. So notice how long the first epoch took over here. It took a whole 50 seconds more than the second epoch because it was trying to map a function to all of the data in one hit. Now, why is this important? If we could save 20% of our training time every time by just efficiently loading data, well, wouldn't you want to do that? You ready to rock? Same model, same amount of epochs. Let's do it. Shivans, love watching my stuff. Thank you very much. I really appreciate it. Let's see how long this first epoch takes. Oh, we got an error. Whoa. Okay. Cannot batch tensors with different shapes. Alright, so we need to reshape first. I've got an idea. We create two separate pre-processing functions. Def, reshape image. image equals TF, image, resize, image. Image shape, 224. We're getting really hacky here, but this is why it's fun. Return image, label. So we're going to run the reshape image first as a mapping function, then batch. Oh, this is going to be dope. We need to reload our data loaders. All in the name of science. This doesn't scale our images, does it? No, it doesn't. Converts, I'm going to get rid of that. And this is converts data type. That's all right. Okay, now what we need to do is map reshape image num parallel calls equals tf data auto tune, then shuffle, then cache. Then we want to map. Yep, this is what's up. Look how advanced we're getting with our data loaders. Simple is best, Daniel. Oh no. Our test data has a boo-boo. Need to reload the test data. Where is that getting? Oh, here we go. Every time we make an error, because it gets saved in memory, okay, that's what we want. Now, will this beat this time over here? Always see how fast you can get your data. You ready? Let's see what happens. This is the time to beat. Watch our RAM. Does the RAM go up? RAM slowly going up. Can you see that? I'm not sure. Oh, RAM's exploding. Is our notebook crashed? Your session crashed after using all available RAM. Okay, so this will only work, caching will only work if you've got a small data set to fit in RAM. Let's write this down. Tried to cache with a large data set. Didn't work. Caching only works if your data set fits in RAM. You're totally right, Topu. Imagine, if I had a lot more RAM, that'd be way better. But Collab, it caps out at 12. And I mean, I think my computer has more RAM. It has 64 gigs. Yeah, look at that. My Mac has 64 gigs of RAM. After the course, I need to rerun all the variables. After I finish the TensorFlow course, I'm going to get really into my deep learning PC and build an epic project. Super fast data loaders, super fast model training code. Do I have to download this data again? Please tell me not. Oh, thank God. Thank you, Collab, for caching the data. Even though I killed all of your RAM. So I can't cache it because my data set's too big. I think my deep learning PC, which is downstairs in the kitchen, I'm currently in the process of working out how to build an SSH bridge just between them. It's probably pretty straightforward. I've just never really done it. And I've had other things on. So that way I'll be able to SSH from this machine, this is like my home office studio. And I'll just have my deep learning PC running downstairs and run stuff on it there. So caching doesn't work unless you've got enough RAM. Good to know. But at least we tried it firsthand, right? That's the important thing. We just didn't read docs. We're actually running experiments here so that we know firsthand knowledge. Knowledge. All right, let's see how this goes. Time to beat is over here. RAM shouldn't explode this time because we've got rid of the caching. But imagine how fast it would have gone if we did have enough RAM. Yeah, I've got Ethernet cable won't work because I'd have to run it like up these stairs, and then I don't know if you can see, but there's like a set of stairs just over there, and I'd have to come up those stairs through here into this room. Maybe I could go up there, but that would just be a pain in the ass. So I'll just use Wi-Fi. Oh, what? Oh no, that's from before. I thought that I crashed the RAM again. Okay, let's see this. But this, if it doesn't improve it too much, I mean, okay, you could probably step through this pretty easily. Like, that kind of makes sense, doesn't it? We reshape the images first, then we shuffle them, then we batch them, then we pre-process them, which is, pre-processing is converting them from int8 to float32, because when you download them from TensorFlow datasets, they're in int8, and our models need float32 or float16 mixed precision. So let's see if the time makes any difference here, batching after mapping. But we just realized I need to write this down here. Actually, I'm going to put this, because this is the notebook that we're going to choose to publish today, once we've prepared it a little bit more. TK batch and prepare datasets. Things to note: can't batch tensors of different shapes, e.g. different image sizes. Need to reshape images first. Can't use cache unless your data set can fit in memory. Num parallel calls equals tf data auto-tune will parallelize pre-processing and significantly improve speed. I think that's, prefetch helps to increase speed to get one data batch ready whilst the other is being computed. So they're just some tidbits. How are we going for time down here? 230 seconds, so it's about the same, no matter what order we go in. What did we get down here? Okay, the next step will be mixed precision. Do we do a mixed precision test? Oh, that failed. Okay, let's try mixed precision over here. We're figuring this out once and for all. Okay. Do we see much of an improvement here? Yeah, you're right. Once I've got it, French Toast Mafia, connecting everything, like the deep learning PC and whatnot, that'll be a great video idea. So I'm taking notes on how I'm doing it. Because that way, I'd like to just be able to, that would save a lot of like processing power on my current machine. So then I could just write code on here, which doesn't take much processing power at all. And then if I ever need to compute something, just like if you were using a cloud instance, I would just send the compute down to the deep learning PC, and then it would just run all the compute stuff down there. Yeah, so in fact, we might have created a little bottleneck by reordering the mapping functions. That's all right. Now let's compare mixed precision training. So this is where you have to also work out what to do while your models are training. We're working on a larger data set today. Fine tuning. We're not using data augmentation anymore. Yeah, so this will be good. Okay, so that mixed precision first epoch was pretty quick, but so was this one. And I think our data's already loaded as well, so that's why it might be a bit quicker. Be interesting to see how long this second epoch takes. And here we're not really seeing, okay, so this is how I kind of like to teach things as well, is go for the simple option. And then, because you can always add more complexity as needed. And people, if they're interested enough in learning more about something, will always seek out their own next steps. So if you can lay good foundations, get someone interested in something, they will learn the rest themselves. Whereas the way we're kind of education is too often you think about, oh, the teacher should teach me everything. No, a really great teacher will instead get you interested in a subject, and you'll end up teaching yourself. And then you'll bounce what you found off the teacher. Because the best learning is kind of going back and forth in a conversational style with someone who knows a little bit more about you. A little bit more about a topic than you. Okay, so mixed precision actually doesn't change too much here. If our data loading is efficient, and I'd really love to be able to see how much GPU utilization it is. So how could I do this on Collab if I don't have a terminal? How to see GPU utilization in Collab. Ah. So true. Can just use weights and biases. I'm going to log into weights and biases. Why did that go off the screen? French Toast Mafia, yes, you're entirely right. NVIDIA SMI does that, but I can't run NVIDIA SMI whilst my notebook is running, unless I had a terminal interface. How did I sign into weights and biases? With GitHub? Ah, we're on. Okay. I'm actually going to stop this one. And I'll stop this one too. No, I'll run it over here. I'll load this over here so that it doesn't put out the access code. Holy crap. This is amazing. Let me show you what this looks like. How do I get rid of these chat things? Okay, GPU utilization, boom. Okay, let's see how, let's run some code. Copy of a copy. Rerun this, rerun this. Does this go over to here? Oh, we're on. Look at this, guys. This is really cool. GPU utilization. Oh. So we're not... We're not fully utilizing the GPU. We've still got heaps of memory left. So what does this tell us? Well, we could maybe increase the batch size. That's cool. All in a couple of lines of code. Okay, but this is the notebook we're focused on. So are we going to use mixed precision? No. Oh, mixed precision did give us a speed up for fine tuning. I need to turn mixed precision off and then fine tune. All right, that's our experiment we're about to run. Let's see how much mixed precision saved us. We'll make every layer trainable in the base model. And we'll give it a 10 times less learning rate. No, we need to turn mixed precision on. Turn on mixed precision. Turn off mixed precision. So the experiment we're running now is, in a previous stream, we fine-tuned our model with mixed precision turned on, and we found it got us a really good speed increase. But now we didn't actually compare it with mixed precision properly turned on, off, and proper data loaders. So that's what we're doing now. Let's load 32. So with mixed precision turned on, fine tuning really helps. No. No. This is what we did wrong. We need to use our mix model. That should be results. Beautiful. Okay, so this seems a lot quicker. Let's go back to our copy of a copy. I'm going to test it over here. The prefetching of data is what's seeming to give us the best results here. So let's rebring this over here. If you have efficient data loaders, that I think is your biggest savior. I'm going to restart the runtime. So this one will be without mixed precision, which I'm fairly certain we did yesterday, but that's all right. Wow, that actually went pretty quick. We'll wait on this one to load. So after this experiment, why doesn't Spotlight index my applications folder? There's a notebook here. Map, shuffle, batch, prefetch. Okay, beautiful. Yo, Sheik, how you going, my friend? We're getting this notebook ready for publishing, number 7. We've just done a whole bunch of experiments on caching and prefetching data sets. It turns out cache only works if you have a data set you can fit in memory. But we've worked out how to save us a lot of time, ourselves a lot of data loading with map, shuffle, batch, prefetch. And we've also been diving into the TensorFlow documentation. Oh, we saw weights and biases, how it is measuring our GPU utilization. So that's very cool. Making sure we're using as much of the compute as we have on offer. And we drew this beautiful diagram. The CPU is slow, the GPU is fast, and we want to use prefetch to help minimize the time between CPU and GPU. Want to minimize the time going back and forth, get stuff from CPU to GPU as fast as possible. And we've been looking through the TensorFlow best practice for loading data, and we've been basically re-implementing that for our own data sets, which is very exciting. Is this still running? Oh no, I don't think we initialized it. That's all right. So I'm going to let this run for a second. And then what else did we need to do? Clean up headings, clean up model loading, access cell outputs, runtime, the experiment we've got going here as well is we're coming back to our previous notebook of 07, and I'm training a feature extraction model here, and then I'm going to fine tune it without mixed precision turned on and see if, because we've optimized our data loading now, I want to see if the speed up benefits we're getting are from mixed precision or from optimized data loading. So I think yesterday we kind of worked out that mixed precision offers a little bit of improvement, but data loading also offers an improvement. So we want to see what the difference is between the two. I'll be back in a sec. I'm going to get some water and go to the bathroom. It is, my friend, it is. How cool is this? It's going to be on the course of Chic, you're very right. That's what I probably will do for the rest of all of the rest of the modules, is just live stream them. I mean, does that take away from the surprise of what you'll see in the course? The course videos will be way more refined than the Twitch live streams, of course, because I'll have figured it all out by then. But the Twitch live streams will be like us figuring out how to do things the best way together, and then we can turn it into some solid material. But by the end of this live stream, whenever that is, today or something, probably go for at least another hour and a half. I'm going to commit this to GitHub, and then you can run through it and try it out yourself if you really wanted to. But yeah, I want to make sure that this notebook runs really well. But yeah, how's your day, man? What have you been working on? So this is the code that we're running down here right now. And I think what I'm going to do for number 7 actually is I'm going to go through an example of using the data loader to get the data in, but I want a student to try and build this model by themselves, because by the time they get to notebook 7, they'll have built many different TensorFlow models. And so rather than me sort of going through yet another model building experience, I'm going to only just talk about loading the data and making it fast. And then I'm going to set it as a challenge for a student to go through this themselves. That'll be their milestone project 1. So I'll have, for section 7, this is what I'm thinking. I'll have a notebook like this with all of the code and all of the text, like showing you how one way of doing it. And then a notebook which is just basically all headings and just says, write the code yourself. So it'll be like the ground truth and then the template. And the assignment will be for the milestone project 1, go through the template and try and do as much of it as you can. And if you get stuck, look at the example notebook. What do you think of that? Because up until this point, we've been just basically coding everything together. But I want it to start being, hey, you got to give this a go yourself. Does this notebook have a T4? Otherwise, we're fucked. Can I swear on Twitch without getting banned? I know YouTube get angry at that. Oh my god. An earthquake 8.0 hit near NZ. Now a tsunami is expected. Did I feel anything near Oz? No, I didn't feel that. I didn't even hear about the earthquake. NZ earthquake. What is that? Is that a wave? Wow. I wish that was better quality. Wow. Wow, that's a tsunami in New Zealand. Oh my goodness. No threat. Oh, I'm safe. So I live about here. I live here, Brisbane, New Zealand, earthquake was over here. So I'm safe, but that's crazy. Here we are coding TensorFlow. Okay, we've got a T4, so mixed precision will work on this one. They're beautiful. Is that what we were testing on here? Yes, it was. No, we want no mixed precision on here. I'm going to uncode this. And then Shaking Basket says, do I stream every day? I've streamed for the last 3 days. Have we, Ashik? I've streamed for the last 2 days. So this is the 3rd day in a row I've streamed. I'm probably going to do a lot more live streams going forward because that's just the easier way for me to make content, is because it's and also the streams are real, right? You see me coding as I'm writing the code. It's not like I'm making some YouTube video and editing it and you don't see the fact that it took me 4.5 hours to work out one small thing. Like, I'm trying to work this out as I go. So I want to do more live streams. No, she definitely use transfer learning for this problem. Like, building it from scratch does nothing. I would definitely use EfficientNet. But yeah. So, Shaking Basket, thank you for that. Yeah, you can see how I think too. Now, I'm going to tell you straight up, I'll be the first one to tell you, I'm definitely not the best coder, I'm definitely not the best one at machine learning, but I'm trying to figure this stuff out. Just like everyone else out there. So set all the layers to true. We're not using, so we ran some experiments and we found that data augmentation actually doesn't really help our model in this case. Model layers, we're doing mixed precision off on this one. All right, who's ready to get inverted? So this is, I think I'm going to save this. With a whole bunch of warnings, they can get out of here. But, Shaking Basket and Ashik, yeah, let me know. I'm looking into reposting these streams just exactly as they are. So if I stream for 4 hours straight, I'll take that entire stream and upload it as a YouTube video on another channel called like Daniel Burke Streams or something. And I'll just upload the whole thing there and people can watch them later on if they want to. I'm not going to edit them because I don't have time to sit through and edit 4 hours of coding. But if someone just wants to watch it in the background or something like that, they will be able to. So let me know if that's something you'd like to see. And I think I've got an idea of how I can upload them to YouTube. We're going to run this again. This is without mixed precision. Because not everyone can tune into the live streams, you know? Ah. So mixed precision helps an outstanding amount for fine tuning. I need to write that down. Mixed precision training Did I write this down? We worked that out. We have worked that out. So I'm going to put this here. Mixed precision helps an outstanding amount with fine tuning. The more model parameters you have, the more mixed precision seems to help. Make sense? That would be massive, yeah. Daniel Burke archive. You're totally right. So let's do that, hey? I'll make another channel called Daniel Burke Archive, and I'll just start uploading all these streams. So mixed precision helps an outstanding amount with fine tuning. Look at this. $784 seconds for fine tuning without mixed precision, and this one was with mixed precision. 300 seconds per epoch. Crushed it. And let's see how our model goes compared to deep food. Remember, this is a paper that we're beating here, by the way. We're not getting state-of-the-art results, but we are beating a published paper. State-of-the-art results. Oh, meal snap. Meal snap. Is this a thing? Doesn't work anymore. Why did they close their app? Eatly. Not available. It worked. 79% accuracy. And they got 74. Holler at your boy. Okay, that fine tuning. Look at my fine tuning results. This is with data augmentation and without proper data loading. So that took 1,400 seconds versus when we optimized our data and we turned off data augmentation, 308 seconds. So we reduced it by 4x. That is insane. Okay, let's start tidying up this notebook and keep letting this run. We've worked out that you'll want mixed precision on. So this is what we need for notebook 07. Use This is what we're going to do. We'll start from the top. Clean up data loading. Clean up headings. We want to use mixed precision training. I think we need to clean model loading code as well. That can actually go here. Right? So let's start on this. Runtime. I should save a copy of this notebook before I start hacking it. But I've already got copy of a copy of a copy. So let me okay, there we go. So now, did I restart the runtime? Yes. So I'm going to put here to do, and then just copy over this to do. So I'm thinking what I might need to do is introduce mixed precision in a quicker way in between this notebook and 6. So maybe 6.5 could be like a bonus and going introducing mixed precision or something like that. Because otherwise you have to get to the you basically have to get to the end of the notebook to figure out mixed precision. We'll start writing the code and see what happens. NVIDIA, we don't want download data. We're going to also use TensorFlow datasets. TK means to look at later, by the way. Like we're going to use in okay, beautiful. Now I'm going to go back through my notebook and make sure all of the code runs. So this is how I make out materials for the course. I write all the code myself, and I do heaps of experiments like what we've gone through now. And then once I've got like a really rough amount of code, I go back through it all and I make sure that the code runs from end to end. And then I start going back through and adding text around explaining the code. And then finally, I go back through the video and I talk through the code as we write it. So this is me going back through the code and making sure that it all runs. And if it all runs, well then I'm going to save this to GitHub and you'll be able to see this notebook. Get class names, TK, getting class names from TensorFlow datasets. Dataset requires downloading the dataset info parameter using the as supervised equals true parameter in the TF-DS load method. Text. Exploring Food 101 data from TensorFlow datasets. So if you have any questions about what we're working on or what we're making, leave them in the chat and I'll get to them eventually. But otherwise, I'm just going to start running through this code quite fast, because this is also where I find errors, right? Models, so it's all, this is massive thing with TensorFlow models or any deep learning model is all different size tensors. Models like float 32 data, and scaled data between 0 and 1, not scaled between 0 and 255, and yeah, so massive thing is getting your tensors in the right shape and in the right data type for models. This is probably one of the, once you've got your inputs and outputs of your model, because of the power of transfer learning and pre-built models, you'll probably spend most of your time there. So a lot of people put a lot of emphasis on how do I build models from scratch. Okay, yes, that's important. But if you want to get great results, spend most of your time getting your inputs and outputs of your model ready, then use transfer learning, and then you can iterate from there. That's going to give you the best results to start with. And models like batches require all tensors of same shape, e.g. all images in. So right now I'm going through and just writing myself notes of what I'm going to do, and simultaneously, so this doesn't actually scale the image. Now, because we're using EfficientNet, it has rescaling built in. Note. EfficientNet. TFCare is it layers.experimental? Layers experimental, yes it is. Okay. Like the one below. Wonderful. That's working. That's what we want. Fish and chips. Oh, delicious. I wonder if we shuffle to 10,000, what does that happen? Does that have much of an effect? Have we got this? So we need map, we need the order. Steps to go through. Map. What does? And then we go through shuffle. What does? And then we go through batch. What does? And then we go through what does? Extra cache if your data set is small enough to fit in memory, or you have lots of RAM. Collab only has 12 gigabytes of RAM. Beautiful. Now, I believe we have a function. Did we import our helper function script? No. This notebook is coming to life. Where were we up to? Create modeling callbacks. TK. How's our... Yeah, look at this. We've done a whole bunch of stuff, and our model over here without mixed precision is still taking forever to train. So we definitely need to use mixed precision for this notebook. Thank you, Topu. I really appreciate it. Thank you. Enjoy your night, my friend. Ashik, these are the steps of transfer learning for computer vision, isn't it? For NLP, it will be very much the same. You're right, yeah. What I'm trying to teach as well in the course is steps that you can use across a lot of different projects. So the experimentation, that can be used a lot across all the projects. So like you start small, and then this is the largest like project notebook that we've worked on so far, but it's also the 7th notebook we've gone through after covering like 180 videos. So it took us 180 videos to get to this point. So we started very small with a binary classification problem, and now we're working right up to working with 101 different classes and building our biggest model yet. So that's where we're at. We're not using data augmentation. Yeah, Ashik, you're right. There's a fair bit more nuance that'll go with like GANs or style transfer, but the main thing I'm trying to get across throughout is experimenting and getting your data input and output shapes where you want them to be. So, and I also can't cover like all the different types of models like GANs and style transfer, because personally I don't have the experience with GANs, and secondly, I mean, if you try to include everything in a single course, it would be far too long. Okay, we're up to retraining our feature extraction model. So let's see how this goes. We should get very similar time steps to what this is. So we'll have to wait for this to go through. Yeah, so see here our RAM is increasing. So because our data set's performing some mapping functions, I think that's why RAM's going up. And if we had enough RAM, we could cache everything. Oh, is our RAM going to explode here? 7.969 gigabytes out of 12.7 gigabytes. Oh, our RAM's turned yellow. We might be in for a RAM explosion. Oh no, why is this going up so high? Oh, we're on. And boom. Okay, this is good. This is good. It's not taking too long. I think OpenAI released another blog post today. Let's check that out. OpenAI blog while this is running. Oh, multimodal neurons in artificial neural networks. We've discovered neurons in CLIP that respond to the same concept, whether presented literally, symbolically, or conceptually. Oh my goodness. This may explain CLIP's accuracy in classifying surprising visual renditions of concepts, and is also an important step towards understanding the associations and biases that CLIP and similar models learn. Ah. So CLIP is a general purpose vision system that matches the performance of a ResNet 50 model but outperforms existing vision systems on some of the most challenging data sets. Each of these challenging data sets, ObjectNet, ImageNet Rendition, and ImageNet Sketch, stress the model's robustness to not recognizing not just simple distortions or changings in lighting or pose, but also to complete abstraction and reconstruction sketches, cartoons, and even statues of the objects. Wow. Biological neuron. Our discovery of multimodal neurons in CLIP give us a clue as to what may be a common mechanism of both synthetic and natural vision systems, abstraction. We discover that the highest layers of CLIP organize images as a loose semantic collection of ideas, providing a simple explanation for both the model's versatility and the representation's compactness. Oh my god. I'm going to put this over here. This is going to take about 5 minutes to run anyway, so let's... This is a spoiler alert for an upcoming Machine Learning Monthly, I reckon. Oh, wow. The biological neuron. So, neural network. So this is saying that there's some sort of neuron. You imagine a massive neural network that was trained for OpenAI's recent CLIP model. So it's saying one of these neurons is learning Halle Berry, sketches of Halle Berry, and texts of Halle Berry in one neuron. That's insane. CLIP neuron. Oh no, this is a biological neuron. Okay, so this is your brain, and this is CLIP. Spider-Man in costumes and spiders. Responds to comics of Spider-Man. Responds to the text spider and others. Previous artificial neuron, Neuron 483, generic person detector from Inception V1. Responds to human faces. Wow, so CLIP is very close to biological neurons. This is insane. If you want to read on with this paper, team. Yeah, Sheik, you can skip around the course as much as you want, but just remember, the course is a little bit designed to go in sequential order. But if you're comfortable with the regression part, you can go on to the computer vision part. Holy crap. Look at this. This is what's inside a neuron. Text, face, logo, architecture, indoor. Oh my god. This is like out of a dream. What the hell? This is some trippy shit. I want to take acid and look at this blog post. This is what the neurons are saying in clip. Oh my god. Is this real? Selected neurons from the final layer of the 4 clip models. Each neuron is represented by a feature visualization with a human-chosen concept labels to help quickly provide a sense of each neuron. Labels were picked after looking at hundreds of stimuli that activate the neuron in addition to feature visualizations. Piggy bank equals finance plus dolls and toys. Oh my god. Barn spider equals Spider-Man plus animal. I'm tripping out on this. You can turn it into a piggy bank by just putting cash on it. This causes the classifier to misclassify a standard poodle as a piggy bank. What the hell? That's crazy, man. Dude, if you went to like a shaman and they showed you this stuff, you'd be like, yeah, alright. But this is legit scientific research. Attacks in the wild. We refer to these attacks as typographic attacks. We believe attacks such as those described above are far from simply an academic concern. By exploiting the model's ability to read text robustly, we find that even photographs of handwritten text can often fool the model, like the adversarial patch. Oh, you want to turn an apple into an iPod? We put a label saying iPod on this Granny Smith apple. The model erroneously classifies an iPod in the zero-shot learning session. Oh, wow. Oh. Level 1. That's a good meme. First gen first gen multimodal models be like, that's funny. I love that image. First gen multimodal. That's literally my iPod. Ashik. I need to get you an iPod, my friend. Oh, that's a really cool blog post. That's going in, that'll probably go in a future video, episode of Machine Learning Monthly. Alright, so we've got a few more seconds to train up on here. Why is this taking a little bit longer than before? Is it because we've got a callback running? Model checkpoint. Yeah, alright. And we've got our data loaders correct. You know why? Because I think we shuffled 10,000 instead of 1,000. I'm going to switch that back to 1,000. And you know what we're going to have to do as well? Is change the model architecture. That's what we should have done. We should have made it that's what we also need. That's what we've missed out on. But can we do that down here? Wonder if you can change the layers. Will there be more health videos? Yeah, sure. I have been meaning to make more health videos. Anything in particular you'd like to see, Ashik? Let's move this one back. Stop. Or more like a long video on how to balance ML and health. That's a great one. Yeah, see, if we don't use mixed precision, we're going to wait a very long time for our model to train. Oh, I ran out of RAM. Oh, I have to reload everything. See, this is why I like to run through the code end to end. Ashik, I need you to do me a favor. When I save this to GitHub, open it up in a Collab notebook and then just run through it end to end. It should run. It should run. Wonder if NVIDIA 3060 is available. Okay, so watch the RAM. 2 gigabytes of RAM used. So the quick answer for that on how I balance ML and health is that health is number one, like my priority. Like remember when last time you got sick, right? What happened? All you wanted was to be healthy. So I've kind of learned that lesson enough times to go, you know what? If I'm working too much or if I'm feeling a little run down, I figure out health from first principles and start to take care of myself there. Where's the deep learning stats? Wow. Look at that streaming setup. Is that something that I need? Am I a Twitch streamer yet? Imagine if I had this stream set up. That's some serious gear. I'm pretty close though. I've got the 2 monitors. I don't have the NVIDIA powered. I don't have a mouse. I don't have all that red and green stuff. You know what? I may be doing more late night streams when I start to work on my projects. Do Twitch hackathons, you know? I think we spoke about this in yesterday's stream. That's a good looking card. Where do you buy it? See all buying options. You might. How much is this in Australian dollars? What do we reckon? Where's search? Oh my god. Nope. I just want to search. 3060. Oh, 800 bucks. That's not even too bad. 12 gigabytes. It's got 12 gigs. The 3060 is a beast. Ha 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 ha. Yeah, so this will be interesting to see. Our last experiment with this ran at 220 odd seconds because we tried to shuffle 10,000. Should I have turned mixed precision on at the start? Nah, it'll be okay. Yeah, that's, if you're getting sick every month, that's why you definitely need to sort of reset and take a look at your health from first principles. And by first principles of health, I mean first principles of health, you could have food. What do you put in your mouth? Sleep. Do you get enough rest? Movement. Do you move your meat body enough? Nerds like us sit down at computers for long periods of time with no movement. Need to counteract. What else is there? Sleep, food, movement, spirit. Are your relationships tuned in with yourself and with others and with God or whatever higher power you believe in? Maybe AGI. And what else could you say that there is? Stress. Get rid of that shit. Throw it into the can, into the trash. So these are like the first principles of health. Food, sleep, movement, spirit, stress. You don't have to overcomplicate it. So food, you keep it simple. Are you eating junk shit? If you're eating anything that looks like this, standard American diet. Avoid. Avoid this junk at all cost. Standard American diet. You know what it is? It's called the SAD. SAD. Avoid this stuff. Eat stuff that your grandparents would recognize as food. Standard American diet. Sleep. Do you get enough rest? I think everyone can get more rest in this age. We all look at our screens too much, and I'm guilty of this as well. Movement. I do simple movement. I go for walks basically every day, every afternoon, every morning. Fresh air. Love it. And I also do a lot of weightlifting and fighting. So walks are very chilled out. No phone, no nothing. I'm just enjoying nature. Fighting and weightlifting are very intense. My heart rate is very high. I'm sweating, yada, yada, yada. Spirit. Are you doing things that help your relationships with yourself and with others, with God, or whatever higher power you believe? If you have great relationships, it will help reduce stress, because stress is the big killer. Over a number of years, once stress builds up, it forms like this little ball in wherever in your body, and then suddenly that ball gets big and then just takes over all your systems, fucks your shit up. So remove stress. First principles of health. You're feeling down, refer back to these. See, this is what you come to these live streams for. Not only do we speed up our TensorFlow data loading code, but we talk about the first principles of health. And this is nothing new. It's not like I'm some guru spitting out this stuff. This is quite straightforward. If you think about health in terms of a physicist, how would a physicist look at health? What else can we look at while I'm models training? Do we get to see any gaming? I used to be a big gamer. I wonder if this is my original YouTube channel. I posted games on there. Lord Rangers. Yes, this is me playing RuneScape back in the day. Lord Rangers first vid. 2008. Oh yeah.
I like to move it. I like to move it.
I'm gonna get banned. Look at that, unregistered hypercam. There's Lord Ranger, there's a beast. Just practice, I know it's shithouse. I need to learn more about Movie Maker. I was 15. I'm gonna like that. It's my first ever YouTube vid. Oh no, I think there was some more back in the day we posted of fireworks, homemade fireworks, and I think they got deleted because YouTube don't like to post homemade fireworks. But check out this, first ever YouTube vid. Boom. I gotta subscribe to myself. Subscribe. That's how you get started. Why did I ever stop making vids? Imagine if I was making vids from 2008. That would have been sick. Where are we at? We're at the stream. Have we done what we need to do? Clean up data loading, clean up headings, clean model loading code. So we actually have to wait for this to finish. I'm going to get rid of this cell. So I think I want to do mixed precision training before. I want to turn on mixed precision before we do the feature extract. We'll run this later. Yeah. Did we need to feature extract for 5 epochs? I don't think so. Maybe we could get away with 3, but we'll leave it at 5. So where do I want to get to? I want to get to at least down here. And in the next stream, which will probably be next week, we're going to really finish up this notebook. Oh, so close. I'll be back in a second. Old Greg. What's happening, old Greg? Alrighty, here we go. We're on to the next step. Beautiful. So, for the actual course, I'm going to save the trained models that I've trained in this to Google Storage so we don't have to go through training over and over again. It'll be like the classic, here's what we prepared earlier. How long have we been going for here? Nearly 3 hours? This is good. This is a good stream session. Our model's performing pretty damn well with just 5 feature extractions. And EfficientNet B0, by the way, we could upgrade this to EfficientNet B4. Don't actually need this. Wherever we can save a line of code, we want to. I'm going to clean the absolute crap out of this notebook in a future video, future stream probably. Wonderful. And I'm going to run this. Oh, Ashik, why don't we use ResNet or another pre-trained model? Well, as you'll see, this is a spoiler alert for what you're about to come up to. We did an experiment in Notebook 4 comparing ResNet versus EfficientNet, and we found EfficientNet blew ResNet out of the water. So we chose to use EfficientNet. This is why we got EfficientNet. That's a spoiler alert, by the way. Okay, now I want to make sure I've got mixed precision turned on. Now we'll go from checkpoint, loaded checkpoint model. Did it not save a checkpoint? TensorFlow load model from checkpoint. I thought that should recognize. Oh. Okay. That's what we didn't do. We need to save a model checkpoint path. That's all right. I'm saving a model to drive here. Downloading a model and from GS and using it in this notebook. Load model previously saved above. Yeah, I wonder what this... Wow. 87%, that's pretty good. Place 2,777th, and first place got 91%. Did they release their code? What they used? Beautiful. Loaded model working. Yeah, these guys are having a lot of problems too with the save model format. custom gradients. So I think this is an error with the EfficientNet application. As long as it's still working here. Now we're up to fine tuning. Output, softmax, activation. No, we want to turn mixed precision on. All right, we ready? This should work. And pretty darn quick. Oh yes. That is dramatically going lower and lower. Please keep going lower and lower. I think it may be because we've just loaded our model back in, but we'll start to let this run and we'll get rid of all this crap. TK, fix what? Looks like we're not using mixed precision. Gonna reload in the model. Yeah, 3 hours straight streaming. Pretty big session here. Because we want to get stuff done, you know. Mixed precision training. How do I check that the first layer in my model is using mixed precision? There we go. Model.layers dtype policy. Oh, this is what's up. Ah, here we go. So they're all still using. What if I try to change? If you reload a model, I think you need to change. What if we layer what if we manually set So I think because we load in our model from file, we can't change its D-type policy. Very small toy models typically do not benefit from mixed precision. Each layer has a policy and uses the global policy by default. TensorFlow, how to change a layer's D-type policy. See the mixed precision guide? I don't think we can do it on a loaded model. Set global policy. And what if I load it after I've set the global policy? So my issue is, because we've saved and loaded our model, its data type policy isn't working. So there we go. So that's what we want. Well, sorry, that's what we don't want. So the model is load in a saved model for fine tuning. And we have policy float 32, whereas its policy we want mix float 16. So what we might have to do is can all of the model saving. TK looks like saving and loading a model turns off mixed precision. Even resetting the global policy doesn't help our model. Might have to can saving a model in between different data type policies. Yeah, so before, if we want to use mixed precision to speed up our model training, we have to get rid of saving the model in between feature extraction and fine tuning. Because if we feature extract and then save a model, it resets all of the layers and freezes them to float 32. Then when we load it back in, they only use float 32 and can't be changed. I wonder, I got an idea. Let's try to hard code we could hard code the model to use mixed precision. No, that's too many steps. Less but better. So I've got an idea. We should just can saving in between fine tuning and in between feature extraction and fine tuning. So I think we can get away with just feature extracting for 3 epochs, and then fine tuning is going to be where the real work is. TensorFlow use mixed precision with a saved model. Oh, what's the load model got? TensorFlow load. Mixed precision. Yeah, that's what Ashik, that's what I'm trying to do. But if you see here, if I load the model, and then if I have a look at the policy, the loaded model, it's all the layers are float 32 and not mixed float 16. TensorFlow. So I think we're just going to have to feature extract and then fine tune and then save the model. Oh, I wonder if we compile equals false. This might be on, team. All right, let's go back. We're going from the top, team. Yo, Toma. What's going on, my friend? Right now, I am preparing materials for notebook number 7 of my TensorFlow course. And this one, we are training a massive model food vision and trying to take advantage of some really fast data loading techniques in TensorFlow, which are, some donuts, delicious, which are here. So map, shuffle, batch, prefetch, extra, cache, yeah. Beautiful. And we're also trying to take advantage of mixed precision training. But right now we're stuck on, if we save a model that was trained with mixed precision and then load it back in, it gets changed to, we want it to be mixed float 16, but it's saying float 32. So there's our problem. Oh, well, it's still float 32 even if we turn on mixed precision in a freshly trained model. Okay. Oh, what is this? Ah. Okay, so that's working. This is groovy, baby. That's what we want. Tinny TV, what's going on, brother? Ashik, thank you for this link. Okay, yeah, so they had to recreate the model. They couldn't save it and load it. Let's see. That's what we might be able to do, right? If it doesn't work, if saving the whole model doesn't work, if saving the whole model doesn't work, we could just recreate the model and load the weights. But we want to make sure the D-type policy is mixed float 16. Look how many tabs I've got on. I need to get rid of all these. Tinny, we've been writing a lot of code, baby. Writing a lot of code. Deep in the TensorFlow documentation. Holy crap, look how many stars TensorFlow has. So I want to save this because I want to come back to that issue later. So let's see if we can get our... Zeno, what's happening, big dog? Oh! We out here live, baby. Out here live. My eyes are starting to burn. Been writing code since this AM, man. But this is the effort we go to make our models train faster, you know? You spend 3 days working on the same problem. You feel like you get nowhere, but really, you've learned a whole bunch of crap. Sometimes it works, sometimes it doesn't. You know all that stuff? How does efficient debt work? Oh, here's the model. Swish activation function. That's some rockin' Python code right there. And this is mixed precision. Mixed precision equals use less compute memory space to figure stuff out. Faster calculations. Can you see that? Nope. This is mixed precision in a nutshell. Okay, we're getting closer. I've got one more thing I'm going to try and then we're going to end the stream. Yes, sir. Oh. Slowly working towards getting the next notebook ready. I'm going to get something to eat after this. Then I got jiu-jitsu training later on. Is this saving a checkpoint? It is. Fish on. Fish on, Rex Hunt, baby. Alright, 47 seconds left. Who likes this shirt? Heart and bones. That's what you have to... Oh, that's held from first principles. You have to stress your heart and you have to challenge your bones. Stress your heart by doing vigorous exercise and movement. Stress your bones by lifting some heavy ass weights. Are we on? Boom. Not even going to bother with that. Oh, why not? Daniel, use the results tag at the start of each model. And here's what I can do. In loaded checkpoint model. I'm a poet and I didn't even know it. Thank you, Ashik. I really appreciate it. It's good when your talents are recognized. Shit. Oh, is it load weights? What the TensorFlow, how to load weights. Load. Load weights. That's what we could do. New model equals model dot clone. Here we go. New model dot load weights. Here we go. I think this is going to be the last little bit of the stream. Maybe this will work. Oh, if we load the weights, the model stays the same. That is good. That is good. Very good. Very good. Very, very good. Save model. Very, very good. Very good. Now, if we do a loaded saved model, yeah, Coco Jumbo, yeah, pick me up, put me down, put my feet back on the ground. So we just loaded our saved model. We found that the weight data type policy stays the same if we just clone the model and load it. Now, if we do the full saved model method and get fancy, what happens? It's still mixed float 16. Yeah. We've just loaded the model. Now, if I wanted to fine-tune a loaded model, can I do that? True. La 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 la, la 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 la, la 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 la. Yes, these are all trainable. Okay, so now our loaded save model should be trainable with mixed precision. La 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 la, la 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 la, la 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 la. Loaded saved model, compile. Sing the sounds of my people. Loaded saved model. Are we going to get a fast time? So, here's what we want to beat. Model with no mixed precision. Mixed precision should be on. If we go loaded, saved model, we've got mixed precision. Tick, 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 tick. Tick, 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 tick. And then loaded saved model dot layers. It seems like we're on here. This should work. This should be faster. Let's find out. We'll kick the stream off with a finish. Hey, Ellie Lamb 98. Nice to see you, my friend. What's that little hat next to you? Prime Gaming. Nice. Good to see you, Ali Lamb. A sheep. Funny how going through the course everything seems easy. Yeah, well, that's just working. Oh, yes! Sweet victory, but that's how it goes, man. I wanted to make the course top quality. I want to make sure I know this stuff and worked it out. So, if I haven't done it, how can I teach it, you know? Look at this. model with no mixed precision, and now we have mixed precision turned on. What are we getting? We're getting our epoch. It's taking half the time. Cha-ching, cha-ching, cha-ching. What a way to finish off the stream. Now, Sheik, you can go through and verify all of this, but you will have to, I'm going to save this to GitHub. Or actually, I think it's still a little bit busted to save to GitHub. Obviously, you have to change these paths to your own drive path. Okay, so yeah, I'm going to save this to GitHub because why not? I'll start putting some. So it looks like we're updating the repo, but this is good. So mixed precision training. Make sure mixed precision works with the saved and loaded model. But yeah, if you want to, Ashik, or anyone watching this will be on GitHub in a minute. You can go through this. Oh, why is that? Go through this and see if this runs for you. There are some things you'll have to change, of course, which is the paths to drive, but most of this should run. I wanted to make top quality stuff here. Where's our model? Is it still fine tuning? We've got so many headings. Fine tuning. Fine tuning, there we go. Woohoo! We're gonna beat the deep food paper. So fine tuning, we just saved ourselves a lot of time. 2.5x amount of time with mixed precision training on. Yeah, I'm gonna save this. So by the time this notebook comes out properly, well, it's going to be on GitHub in a second. You'll probably see it up here. By the time this one comes out properly, there'll be a trained model here that you can download from Google Storage and just plug and play so that it doesn't, you don't have to sit through all this training stuff. But that's part of your introduction to deep learning, is sitting through the training and figuring out what to do while your model trains. You could do push-ups, you could do star jumps. You could go for a little walk. But we're nearly at the 4 hours. This has been a great session. And what is our validation accuracy? 77.4 is what we need to beat the deep food paper. 77.4. And we get... Oh, come on, man. 77.38. Look how close that was. And that was off a total of 5 minutes of fine tuning. Versus this paper took 2 to 3 days. Fine tune, 2 to 3 days non-stop. We just did all of this in like 10 minutes. 5 minutes feature extraction, 5 minutes fine tune, and we get basically the same results as the deep food paper. And then after 250,000 iterations, it starts to overfit. And we could even do more things. I mean, we could use EfficientNet B4 or EfficientNet B7 or something like that. We're using EfficientNet B1, B0. So I'm going to let this run. Loaded saved model dot evaluate test data. Evaluate mixed precision trained loaded model. I think I've already got a notebook called this. So I need to yeah, Ashik, if you go through this, that'd be amazing if you want to give that a go. I'll put this in GitHub, and it should come with a running Collab link, and then just run it top down and just tell me if there's where the errors are. But if you can figure them out like yourself, there will be things you'll have to change, but it should run end to end until you get to the saving and loading of models. That's where you'll run into issues. But what you're looking for when you're doing mixed precision training is that the layer D-type policy is mixed float 16. That's what you want to make sure before you get to fine tuning. You want to make sure it's mixed float 16. Otherwise, fine tuning will take 11 minutes per epoch instead of 5. So I'm going to save this in GitHub. Log into GitHub over here. TensorFlow Deep Learning, and add draft notebook 07 still has errors. Work in progress. And that should be over there in about 20 seconds. So if you go to the Mr. D. Burke TensorFlow Deep Learning repo, hit refresh, boom, 07 food vision. Loading up, opening Collab. Wonderful. Okay, so that is it for the stream today. Thank you all so much for tuning in if you're in the chat. I'm not sure when I'm going live next. It'll probably be, because today's Friday, I've got jiu-jitsu training tonight, and then I've got jiu-jitsu tomorrow, so I'll probably be next week on Monday. But we're going to finish this. That's going to be the next couple of live streams, is finishing off this notebook ready for proper publishing. But the good news is we are now beating the deep food paper in about 10 minutes of model training. How cool is that? So this has been really fun. And we might as well stay around for one more epoch to see if our model gets over the 77.4% accuracy. It's only 10 seconds left. All the best, Ashik. Thank you, my brother. Thank you for tuning in. I really appreciate the questions and the help. And all the best with the notebook. Look at that. Boom. Just beat the deep food paper. What a way to end the stream. Validation accuracy, 78.42. Their best result was 77.4. Holler at you, boy. This is what we learned today. CPU slow, GPU fast. We sped up our data loaders and then we sped up our model training time using mixed precision. This notebook is full of gold in terms of optimizing your TensorFlow performance. I will catch y'all later.